how's everything going?
Good.
This is our last class. It's really sad. How many people here are doing 270 in the summer? Cool. All right, good. So I will probably see some of you. So my plan today was to just basically go through. Did I already hand back homework last time?
Yes.
Okay, good. So my plan today was just to basically go through and review what we've done this quarter and sort of talk about the final exam a little. But if you've got particular questions, I'd rather start with those. Anything that you want to go over again or talk about or anything like that. Everybody's on that side of the room. It's interesting.
Go over Theorem Proving with algebraic truth table.
Yeah, let's talk about Theorem Proving. We didn't do a whole lot with this, but it comes up. So what's our favorite theorem? I don't know. I think this is true. So we'd like to know if this is a true statement, if this expression is equal to this expression, right? The main way that we prove these things in this course is using truth tables. Okay. Sometimes you can prove these things using various rules of algebra. So De Morgan's theorem, distribution, commutativity, associativity, the adjacency theorem, all of these things from chapter 2 of the text. But we can also just prove these using truth tables. So you want to show something like this is true, make yourself a truth table, go through all the possible combinations. And then you want to find the value of this expression, so let's find the value of each term of that. So the and of ABC is going to be 0 everywhere except the end. The and of ABC bar is going to be 0 everywhere except the column the row right before the end. A, B, and C is a 0. And so ABC or ABC bar or A is just this, ORed with this, ORed with A. And that's just going to turn out to be 0 in the top half and 1's in the bottom half. And now by simply commenting that this column is exactly the same as this column in all possible cases, we can say therefore this expression is equivalent to that expression. So that big long thing is equivalent to just A. And algebraically, if we wanted to show that, we might do something like ABC or ABC bar or A. And we can distribute something that's multiplied by an expression. We can also factor things out, just like regular algebra. So this is actually A ANDed with BC or BC bar or, and this is just a 1. Right, because A and BC is ABC, A and BC bar is ABC bar, A and 1 is just A. And then there's some fancy named theorem that basically says anything ORed with a 1 is just 1. Right, so this is A ANDed with 1, and there's another theorem that says that anything ANDed with 1 is just whatever you started with, and so this is just equal to A. And so that's algebraically showing that those two expressions are equivalent. This is doing it with a truth table. Make sense? Yeah.
Can we do a state synthesis problem?
Yeah, definitely. So state machine synthesis. So let's start with, I don't know, you got anything in mind you want to synthesize?
Just
You want to do a gray code counter?
yeah, sure.
Okay, so let's do a 2-bit gray code counter. So we want to go like this. We want to count in that sequence so that only 1 bit changes at a time. So, handful of states. Let me just call them A, B, C, D. And we're going to move from one to the next. And the output in each of these will be that gray code output. So 4 states, how many flip-flops should we use?
2.
Let's use 2. Let's keep it as simple as possible. So 2 flip-flops. What kind of flip-flops you want to use?
JK.
JK, okay. Alright, so let's make a state assignment table. And I'm just going to go sequentially. States A, B, C, and D. And so our key for our diagram is state. And then let's say 2 outputs, Z1, Z0. Alright, so that's everything we need to make a state transition table, or to start a state transition table. And there's no inputs here. Okay, we could add a run input or something, but we'll get the basic idea with this. So no inputs, 2 outputs, 4 states, JK flip-flops. Alright, so let's start with present state. And that's Q1, Q0. And so we have 4 present states, A, B, C, and D. So state A is 0, 0, this is 0, 1, this is 1, 0, this is 1, 1. Next state, well, A goes to B, B goes to C, C goes to D, D goes to A. So this is B, C, D, A. So Q1 plus Q0 plus 0, 1, 1, 0, 1, 1, and 0, 0.
Wasn't state C and D be flipped?
Not the way that I drew it. So we're going from A to B to C to D, and I labeled A is when the 2 flip-flops are 0, B is when they're 0, 1, C is when they're 1, 0, D is 1, 1. So these are the outputs down here,
Those are the outputs,
right?
okay, got it.
Now, if we were smart, right, we would actually number our states so that this was state C and this was state D, and then our outputs would just come from Q1, Q0. But I don't want to, like, do anything tricky here. So we'll do the naive numbering here. So now we can write down what Z1 and Z0 should be. So your outputs are based on your present state, right? So if your present state is 0, 0, your output should be 0, 0. Present state B, your output should be 0, 1. Present state C, that's where your output's 1, 1. And then present state D, your output is 1, 0. Okay, so we're through with this diagram now. All the information on here has already been captured. So what's left to fill in on this table?
Are the outputs based on the current state of Q or the next state?
Outputs are based on the present state.
Okay.
So what's the next piece on here?
JK flip-flop.
Yeah, we need to know the flip-flop inputs. So J1, K1, J0, K0. All right, so we go through and we can just start with Q1. In this state, Q1 is a 0 and we want it to stay a 0. So what should J1, K1 be equal to? Yeah, and this is where a table might help. Right, so JK acts like that. But you can also think of this as, if you want to do this more efficiently, if we know our current state is Q and we want our new state to be Q plus, what should J and K be equal to? We can flip this table around, right? So if Q is a 0 and we want Q plus to be a 0, we want either a 0, 1, which says 0, or we want a 0, 0, which says don't change. Right, so this can get filled in as a 0, don't care. If we want our output to become a 1, we can either set JK to 1, 0, which says make the output a 1, or we can set it to 1, 1, which says toggle the output, change from a 0 to a 1. So this is a 1, don't care. If we want to go from a 1 to a 0, we can either say 0, 1, which is clear, or 1, 1, which is toggle. So that's a don't care 1. And we want the output to be a 1, we can say 1, 0, which is set, or 0, 0, which is don't change. And so that's a don't care 0. So this is looking at if I set J and K accordingly, what does the output do? This is if I want my output to change accordingly, what do I set my inputs to? And this is what we're using when we do synthesis. And you can figure it out, but if you put this on your note sheet and you know how to use it, it's a fair bit faster. So now we can just march through here and just fill in from our table. So looking just at flip-flop 1, we want to go from a 0 to a 0. We should set J and K to be 0 and don't care. Going from a 0 to a 1, we should set J and K to a 1 and don't care. Going from a 1 to a 1, we should set it to don't care and 0. And going from a 1 to a 0, we should set it to don't care and 1. And then looking at Q0, so 0, 1 is a 1 don't care. 1 to a 0 is a don't care 1, and this is where you make all your mistakes, right? But if you're showing your work, it's usually pretty all right. And then from a 1 to a 0, don't care and 1. All right, so there's the whole state transition table. We're one step away from a circuit diagram now, which is all we have to do is come up with equations for Z1, Z0, J1, K1, J0, K0. And that's, you can do K-maps, but with only 4 variables, we can probably fake it. So Z1 looks like it should be 1, and these are going to be based on the present state. So Z1 looks like it matches Q1, right, 0, 0, 1, 1. So Z1 comes from Q1. Z0 is slightly quirky. Should be a 0, 1, 1, 0. What is that expression for Z0 in terms of Q1, Q0? That's an XOR, right? So if either one of these is 1 but not both, then we want Z0 to be true. So Z0 is an XOR. All right, no K-maps anywhere in sight. What can we set J1 equal to get this column of J1 values in terms of Q1 and Q0? Yeah, if we set J1 equal to Q0, there's a 0, there's a 1. This will be a 0 and a 1, but we don't care what these are. So J1 equals Q0 gets us that column. That's pretty cool. How about K1? Yeah, K1 can also be Q0 because there's your 1, there's your 0, and these we don't care about. So K1 is also Q0. What can we set J0 equal to? Even easier. Yes, you're right, not Q0 works. I heard someone say it. 1, yeah, we can just say 1, 1, 1, 1 because those we don't care about. And same with K0, we just set K0 equal to 1. So J0 equals K0 equals 1. We just tie that to VCC through a 5K, through a 1K resistor, and we're good to go. So tie your clocks together. Z1 comes from here. Gets XOR'd with Q0 to get Z0. And then Q0 comes around and feeds J1 and K1. And J0 and K0 goes through resistor to VCC, and that should be your whole circuit. J1, K1, J0. Yep. So there's your state machine. So when you do this on a test, right, definitely show your state assignment table so that it's possible to map from here back to your original diagram, okay, to help with grading. You'll probably be given a state diagram and a key. You will be given, I've already done the exam. So you'll be given a state diagram and a key. So show your state table, and then when you're filling it in, right, doesn't hurt to put down the table that you're using if you're filling in from a table. In case you've got a problem with that, I'd know where your errors come from. But then definitely show everything in the state transition table: present state, next state, outputs, and flip-flop inputs. So those 4 things.
The circuit.
Yeah, yeah.
Oh.
Yeah, I think that's right. Yeah.
Really quick on the other piece of paper, the state one, no, the...
This one?
Yeah.
Yeah.
I I'm a little confused on why on the state table C is like 1, 0 and B is 1, 1, but in the circle C is 1, 1 and B is 1, 0.
So this has nothing to do with the state assignment. This is the value of the two outputs, right? And we want our so maybe I shouldn't have drawn this. This is what we want the outputs to do. This is not how we want the states to transition, right? So we drew this as we want to go from A to B to C to D and back to A. But in each of those states, this is what we want output.
Okay, so we're basing it off that part.
Yeah, so this is Z1, Z0,
Okay.
not Q1, Q0. And this is effectively arbitrary, right? We could have done A, C, B, D, or whatever. It makes no difference. And as I said, it would have been smarter to make this state C and this state D, because then the outputs would match the Q's, and we would have saved one exclusive OR gauge. But it can be effectively an arbitrary assignment. Other questions about that? I got 3 Lab 8s turned in, which is really exciting. All right, so other questions or things you want to talk about?
Can we talk about some potential short answer questions or topics that might translate well to a short answer?
I don't think I have any. Let me take a peek. I'm going to pause the recording this time. You don't have to worry about that.
No short answer.
No short answer. On the other hand, I'm also missing question 7. So the last question is 10, but there's only 9 questions. So if you see that, don't panic.
We have to make up our own column.
Yeah, you have to make up your own question 7.
What is the color of purple?
Yeah, that's a good one. Yeah.
By saying there's no short answer, you don't mean that it's all multiple choice. So
No.
you say citizen.
No, it's all like the midterm. It's doing circuit analysis, designing circuits, doing Boolean calculations, things like that. There's nothing like, write a poem about Verilog or something like that.
I want that. This is really bad. Got this, right?
I think one of my worst school nightmares that I had, this was when I was taking a linear algebra course, was that I did the exam and it was great and I felt really good about it. I was pretty sure I got 100, and then I went back in and I had like a 30 on it. I'm like, what happened? And the teacher took my exam and it was folded up like an accordion, and he pulled it out and it was this big long test, and I had only done the front and the back, so I missed most of it. That was a bad stress stream. So I won't do that to you. Yeah.
I was saying, would there be practice sheets online for us to practice over some of the stuff?
No, but your homeworks are really good practice. So the homework sets are pretty representative of the kinds of things. That and the labs are pretty representative. All right. Well, let's just start running through this. I posted this the other day, and it's got a few things on here that aren't on the test, so they say not on the exam, but I put them on here anyway. So the whole concept of digital versus analog, right? Digital is about discrete values. For us, it's mostly 0 and 1, right? Whereas analog is kind of a smooth, continuous range of values. So engineering 120, we mostly deal with analog stuff in chapter 4. So your voltage might be 2.75 volts. Digital circuits, it's pretty much, it's 5 volts or it's 0 volts. It's high or low, it's on or off, 1 or 0. So digitizing. Less accurate in some ways, because if we use a bunch of these binary values to represent something, if we have 8 binary digits, right, we can represent 256 different things. Well, if we break 5 volts into 256 buckets, right, we can only represent, you know, a few millivolts from one bucket to the next. It's not exact, right? But on the other hand, if we say the voltage is, you know, 11010001, right, as long as we preserve that number, we've always got that same voltage recorded, right? So it's in some sense more reliable, but it's more approximate. So it's the CD versus vinyl debate, right? CDs are in some sense, you know, more resistant to scratching, but they're not as accurate a reproduction of the original sound. So that's digital versus analog. So binary numbers, we know binary numbers as weighted sums, okay, from Engineering 120. We introduced 2's complement as a way to represent negative numbers. And two things to keep in mind about 2's complement. One, the number of bits is really critical. So here's the number 3, written as an 8-bit binary number. If you want to find negative 3, we do this thing where we toggle all the bits and we add 1. So this is negative 3, this is positive 3. If you're told that you're using 8-bit binary and 2's complement notation and you're asked what's the value of negative 3 look like, you got to write down all 8 bits.
When asked on the exam, if it gives you a 8-bit binary, but the very first digit is a 1, will you always assume that it's a negative number?
As long as we're using 2's complement, yeah.
If it says using 2's complement.
If it says using 2's complement notation, write down the value of this in decimal, right? That 1 up there is going to tell you this is negative, right? And so you can find what value that is by just reversing that process. Complement every bit, add 1. You get this, which is positive 3, so the original number must have been the negative of that, which is negative 3. And when we write positive numbers, if we want to write the number 3, we don't write 0, 0, 0, right? We usually just write down that. But if we don't know how many bits we're talking about, we don't know if this is positive 3 or negative something, right? It's only if we write out all these bits and we see this leading bit is a 0, now we know this is a positive number. So if it's an 8-bit question, just make sure you do all 8 bits, even if it's just a bunch of zeros, right? Because they'll turn into ones when you do this complementing. And saying that we have a 2's complement number doesn't mean the number is negative, okay? So this is how we write 3 in 2's complement notation, right? This is positive 3. This is how we write negative 3 in 2's complement notation. It's just the way that we represent negatives.
Can you get some practice with hex and octal conversion?
Sure. What does this number look like in hex?
1.
So hex, remember, we're looking at groups of 4 bits. So our first group is 0, 0, 0, 0.
Oh yeah, okay, 0.
Right, so that's a 0.
0, 3.
That's a 3. So just 0, 3x. All right, what about negative 3 in hex? So 1, 1, 1, 1, 1, 1, 0, 1. So here we need our table. Right, so 0 through 9, we just use the regular patterns that we're used to. So this is going to be F and D hex. And sometimes we use an X, sometimes you see 0x FD, sometimes you see 0h FD or FDH, or there's all kinds of different notations. You might even see FD with a little 16 on the bottom.
Is there any way to know that that's a negative number if you were just given FDX?
Yeah, if the first digit's 8 or bigger, it's going to be negative. If it's 2's complement. Because those are the ones that have a 1 in the least, the most significant bit. And after a while, I mean, you see this and you just think D, right? It's synonymous in your brain. This is always C and so on. That just comes with time. or by going bowling when you're a teenager and keeping score in hex with your friends, because you're geeks and that's what you do. All right, so octal. All right, there's our hex number. So octal, we break in groups of 3. Always start from the right, because remember, there's an indefinite number of effectively zeros on the left. So break this into groups of 3. We wouldn't normally break an 8-bit number. Well, we might do an 8-bit number in octal, but this is why we do hex, because it's a power of 2. But, so 101, right, that's 5, this is 7, this is 3, so 375, base 8. And then if you want to go the other direction, if you have this, right, just write down the 3 bits corresponding to each digit and stick them side by side. But you can also do this as a weighted positional notation. There's no reason to, but this is actually 5 plus 7 times 8 plus 3 times 8 squared. And if you do that, you'll come up with the same value as if you just did powers of 2. This is ignoring the negatives now.
That would still be a base 10 number? Or sorry, a base 2 number?
So if you just took this number in base 2, ignoring negatives, right, and just did 1 plus 5 plus 8 plus 16 plus 32 plus 64 plus 128, you should get the same thing as this. That's slightly magical, but it works. And same thing with hex, it's just powers of 16. So 2's complement, we can also do signed magnitude notation. We don't really do that in here, but we mention it. Signed magnitude is what we do in decimal. If this is the number 23, and we want negative 23, we just put a symbol in front of it, right? So we can do the same thing in binary. We can say 23 is this. We can say if we want negative 23, we're just going to change that first digit to a 1, and that's going to mean negative 23. That's a signed complement, right? We have, sorry, that's a signed magnitude representation. So this is telling us how big our number is, and this is telling us the sign of it. So is it a plus sign or a minus sign in front? We don't usually do that because arithmetic doesn't work very well, right? If we add these together, we're not going to get 0. If we use 2's complement notation, we take this and this and we add them together, we will get 0. So 2's complement works really well if you're building computer circuits to do arithmetic. But sometimes it's nice just to throw a symbol in the front and say this is a negative. So that's what signed magnitude is about. Range of numbers, so 8 bits, you can go from negative 128 to positive 127. Okay, 4 bits, you can go from negative 8 to positive 7. Because you've got an even number of values and you've always got 0 in the middle. So it kind of feels like the negatives get one extra number. But if you think of 0 as positive, then it's the same number on either side. And the importance of using all bits, I already said that. Conversion between decimal, binary, hex, and octal. So converting from those into decimal, just multiply by the powers of 2 or the powers of 8 if it's octal, or convert it to binary and then multiply by powers of 2. Everybody good on going from decimal into binary? Right, divide by 2, write down the remainder, carry the part over, just keep doing that thing, right?
Well, one quick thing about dividing. The very first, the remainder on top to bottom, is the top one the most significant?
So that's a good question. And the way I do that is you're doing your division. Eventually you're going to end up with 0, remainder 0. And that's going to just keep repeating, which means your digits are eventually going to be just a bunch of zeros, right? So these had better be the most significant bits. Because then you could do this a million times and you just have a million zeros in front of your number. If this was the least significant bit, then depending on how far you went this, your number would get bigger and bigger, right? So yeah, most significant bit comes out last. And after you do a conversion, convert it back just to double check, right? You'll see a question where I ask you to do some binary arithmetic, kind of like what you had on the midterm. So take this number, convert it to binary, convert that to binary, add them together, or do something like that. Try to do it faithfully, okay? If one of your conversions comes out wrong, and you add your numbers together, and you know the answer should be 5, but you add your numbers together and you get 15 instead, don't just change your ones and zeros in the answer to be 5, because you're going to end up losing more points that way, right? So if you do a conversion wrong up here, you lose some points for that, but if you use the number that you got here and you add it correctly to this number and you get the correct sum for those, you get credit for that. Right? If you somehow get the wrong sum because you think this is the right answer, right, you're going to lose credit for the addition part. So just work through faithfully. But the binary hex type questions, you can always double check what you're doing. Representing characters in binary, we didn't do a whole lot about. Just realize that, you know, you can take characters and store them in binary. That's what ASCII codes are. And as part of a larger theme, which is we can use binary strings of ones and zeros to represent lots of different things. Right? We can use 7 ones and zeros to represent letters. We can use 16 to represent Unicode characters. We can use 1,000,000 of them to represent a picture. We can make a JPEG or a GIF or a bitmap and store colors and pixels and make a picture. We could store a collection of those and make a movie. All right, binary arithmetic, addition and subtraction, so mostly addition, right? Pencil and paper, add your bits, carry over to the next column, and so on. Not asking you about high-speed arithmetic, none of the stuff we talked about Tuesday with carry save adders and all that. That was all bonus material, so that's not on there. And if you want to subtract, usually we do it by adding a 2's complement, by adding the negative of a number. We didn't talk about overflow, so that's not on the exam, but it's useful when you're adding numbers to know if you got a result that was too big or too small to represent. And there's a pretty simple rule for that. You can find it in the book, but basically if you add 2 positive numbers and you end up with a negative number, you got an overflow, right? And that's how you can detect it. Or if you add 2 negatives and your sum ends up miraculously positive, you got an overflow. If you add a positive and a negative, you cannot get an overflow. There's no way to get something that's too big or too small if they have opposite signs. So now we've talked about it, but it's still not on the exam. Gray codes are just these ways of counting where you change 1 bit at a time, right? And that's not on the exam. Other than you have to use gray code when you label the sides of K-maps, so you should know that. I don't think we talked about binary coded decimal, BCD. Does that sound familiar? So also not on the test, but I'll mention it anyway because you'll probably bump into it in 270. Suppose you want to store the number 375, this is a decimal number, inside a computer. Well, yeah, we can divide by 2 and find remainders and convert it into binary, but that takes a lot of work. Here's a really easy way to store this. Take 4 bits per digit and just write down each digit. So the number 3 I'm going to write is 0011, the number 7 is 0111, and the number 5 is 0101. There's my number 375. And that's called binary coded decimal, or BCD. It's really easy to store numbers in BCD because you just take each digit and convert it. And if I know this is a BCD number, it's really easy to write the number that corresponds to. That's a 5, that's a 7, that's a 3. So the conversion is very rapid. The arithmetic is not as easy though. If I add 2 BCD numbers together, I may end up with something here that's not a valid digit. For example, if I added 375 and 5, this digit here would look like 1010, 10. And so you have to do some extra work to convert your sum back into BCD. But we'll do that in 270. All right, so that's not on the exam. Switches, know how to wire switches. Okay, you will definitely be designing at least one circuit where I'll ask you to also include the switches. So pull up the input to a 1K, through a 1K resistor to 5 volts, take the other end of the switch, connect it to ground. Right, so that's the way to do this. So this is going to your circuit. So at that end, go through a 1K resistor and then use the switch to optionally pull that down to ground. So that's a pull-up resistor, right, as in FPGAs. If the switch is open, this is logic 1. If the switch is closed, this is logic 0. And if you've got 3 switches, make sure that you're not somehow shorting your inputs together. Right, so your easiest way to make 3 switches is just replicate this circuit 3 times. Right, if you try to share this point with all 3, you're shorting your inputs together, right, and then your circuit doesn't work right. So just do this for every switch and you're safe. All right, LEDs, not as tricky. Basically just put a 1K resistor in series. Yeah?
Can you connect all the ground together for the switch?
All the grounds can get connected together for the switch, and all of these 5 volts can get connected together for a switch, but this point should not get connected to this point on another switch, right? Because this is the point whose voltage we're changing by opening or closing the switch. And it's I'm pretty sure it's logically clear to everybody, but in the heat of battle, sometimes you're drawing it and it just seems like a quick shortcut to just take this one point and use it everywhere, right? And it just changes the behavior of your circuit. LEDs, put a 1K resistor in series to restrict the current, and current should flow in the direction of the triangle. So if that's your LED, this is the side that you want to have go to ground. Put a 1K somewhere in series, either here or here, and then this end goes to ground. This is the one that you're driving with a voltage to make it light up. Logic gates, AND/OR, NAND/NOR, XOR, XNOR, inverters, right? We've been doing those. You did those in 120. And we usually just write 2 things next to each other, maybe with a little dot in the middle, or as we use a plus sign, right? All right, and then the 2 main things that we do with circuits, starting from a truth table, going to an equation, going to a circuit. Right, so truth table, like that, and then you go into an equation, either by writing a sum of products, a product of sums, using K-map, simplifying somehow, and so on, to whatever equations you want, and then from there you can go to a circuit. Okay, so that's the circuit synthesis direction. The circuit analysis, you might start with a circuit, forget about the flip-flops here, right? Here's a circuit with 2 inputs and an output. And you can write an equation. Z0 equals the XOR of Q0 and Q1, so you get that. And then if you need to write a truth table, you can put combinations of your inputs and your output and so on. So we can go in either direction. Yeah?
So I get the truth table to equation of circuit, but circuit to equation of truth table.
Oh, like if I said, let me find you a real example. Right, so here's the circuit we want to analyze, right? So first thing you have to do is you have to figure out what's driving these inputs, D2 and D1. So D2 would be an OR of, X and the output of an AND gate whose inputs are, right? So it's just going from here to writing an equation. And if the question said, write a truth table for this circuit, then from the equation, you could fill in the columns of a truth table. Mostly we go truth table to equation to circuit. All right, system diagrams. Make sure if the question asks for a system diagram, you put in a system diagram, right? And remember, that's just the kind of what goes in, what comes out, without any detail for how this happens. And this is useful because if you're designing a circuit, right, you have a system diagram, well, next thing you want to do is a truth table. This is what the inputs of the truth table would be. These would be the output columns. So it helps you know what your truth table needs. Theorem proving, algebraically with truth table, we already talked about. Sum of product, product of sums. I don't know if we need to go over those. Compact form is where you say, like, you know, f equals sum of m1, m2, and m5, right? So it's that shorthand notation. Right, that's compact form. If I ask for full form or non-compact form, that's when you need to write something like, you know, A, B, C bar, or A bar, B, C bar, etc.
If you say compact form, but you don't explicitly say explicit or implicit, can we do either?
You can do either, yeah. So another compact form is just this, and those are equally good. And if you see this compact form, right, if you see plus MD and you see some numbers in there, those are the don't cares. Okay, so the first and fourth rows of your truth table are dashes, basically. Don't cares help you with K-maps, so always take advantage of them. Bless you. So K-maps, yeah, cover your ones for sum of products, cover your zeros for product of squares. Rectangles have to have sides 1, 2, or 4 in length. No 3 by something rectangles allowed. Wrap around on the edges. You can do the super wrap on the corners if you want, if you have ones in all fours. Don't cares, you can cover, but you don't have to. Okay, you have to cover every one at least once. You can cover a one more than once. And you're allowed to cover dashes, but you're not required. So if they help you get fewer rectangles or bigger rectangles, go ahead and include a dash. Otherwise, just ignore them. And if you have a checkerboard, you've probably got some kind of exclusive OR going on. And so your K-map will probably come up with a horrible equation. That's just what happens. All right, NANDs and NORs are complete, so you can build any circuit out of NANDs, you can build any circuit out of NORs. All right, that's a good place for a 5-minute break. And then we'll talk about muxes, demuxes, programmable logic, adders, and then we'll rehash sequential stuff, which is what we've been doing. So there's not a whole lot to say about that. But go ahead and grab a 5-minute break, come back a few minutes before the hour.